when researchers are developing one of the first neural networks. They took inspiration from the ways that neurons in our brain weigh different inputs and sum them to determine whether or not neuron will fire. Several decades later, and deep neural networks have become some of the most powerful machine learning modules we have due to the advent of big data as well as something called universal approximation theorem. However, researchers have recently been looking back to help them solve a new problem using these brain inspired computing methods, often referred to as neuromorphic computing, which involves both hardware and software. And in this video, we'll learn about what neuromorphic computing is and how it helps to bridge the gap between biological and artificial intelligence and what it might be able to do for us in the future. What does neuromorphic computing means? Neuromorphic computing mimics the structure and function of a human brain using artificial neurons and synapses. It enables efficient real-time information processing, enhancing AI with features like adaptability, parallel processing, and low power consumption.
Principles. When discussing about principles of neuromorphic computing, there are three main objectives that get focused are artificial neurons and synapses, spiking neural network, and hardware implementations. To communicate information between various parts of the brain and the rest of the nerve system, neurons uses chemical and electrical impulses. Synapses are the connection between neurons. This procedure is incredibly efficient and quick in real time. Computers that are neuromorphic attempt to match that efficiency. They achieve this mainly by using what are known as spiking neural networks. Neuromorphic computing's main concept is use of biologically inspired hardware like synapses, brain network, and neuron. An example of most frequently deployed hardware is spiking neural networks, SNNs. Unlike artificial neurons is classical AI, SNNs use short electric pulses or spikes for communications. Such a completely memoristic neural network, which has synapses connecting each neuron to 4 input neurons, can be employed for pattern recognitions as seen here. This matching synapses weight may be adjusted supported value by offline training, and the memristor-based network can gather sample frequency from the neural output even on the small scale. Applying this spiking dynamic in the main goal of the hardware designed for effective information processing. Neuromorphic hardware inspired by human brain uses neural network architecture for rapid information exchange. Research demonstrates its ability to handle massive parallel computations, improve processing speed and energy efficiency, and excel in pattern recognition and learning.
Now, let's dive into some information about design strategies and architectures in neuromorphic computing. An artificial neural network, also known as ANN, is a set of algorithms that runs on normal computers and mimics the logic of human brain. A spiky neural networks is simply the hardware similar of an ANN. One-human computers are another name for neuromorphic computers, which have a high-performance computing architecture and capabilities distinct from the typical computer hardware found in the most current computers. One-human computers rely on binary values for encoding and contain different CPUs for processing and memory units for storing data. Data must be transformed between these units in order to calculate. The term one-human bottleneck refers to this. It raises the energy consumption and speed limitations of a computer. Meanwhile, neuromorphic computers have collected parallel processing power, inherently scalability, event-driven, ability to learn quickly, and fault-tolerance computation as characteristics. When discussing about biological intelligence and artificial intelligence, the development of biological intelligence is a result of natural evolution, where living species show amazing through millions of years organisms have developed biological intelligence that enables them to survive and navigate in challenging settings. On the other hand, artificial intelligence is a type of intelligence that is simulated and mainly deal with data-driven learning and task automation. Artificial intelligence, also known as AI, systems are great at processing huge amounts of data and carrying about programmed tasks quickly, but they often lack biological intelligence's depth of flexibility and emotional understanding. Artificial intelligence systems are limited by their built in limitations and cannot fully mimic the subtle details of human thinking, despite their amazing abilities. Now, let's discuss on how neuromorphic computing and artificial general intelligence, also known as AGI, connects together. Neuromorphic computing and artificial general intelligence AGI are interconnected with AGI demonstrating intellect comparable to human intelligence. Neuromorphic computing is ideal for parallel processing, energy efficiency, and flexibility, while AI is primarily developed on traditional computers. To achieve AGI, machines must demonstrate reasoning, planning, learning, natural language understanding, knowledge, and integration. Verification methods include Turing test and robot college student test.
Neuromorphic computing, a highly funded field, offers small size, low power consumptions, and adaptability, making it ideal for various industries. Through combining neuromorphic computing with AI can accelerate deep learning algorithms, train neural networks, and enhance autonomy and intelligence in autonomous systems, potentially revolutionize the various fields. Let's dive into some of the key use cases for neuromorphic computing. Deep learning and neural networks. Neuromorphic computing accelerates deep learning algorithms and neural network training, thanks to its parallel processing capabilities and energy efficiency. This enhances the speed of scalability of AI systems, leading to more accurate and complex modules. Edge AI and IoT devices. Neuromorphic chips are ideal for edge computing and IoT devices due to their low power consumptions and local data processing capabilities. They enable real-time, low-latency inference and decision-making in applications such as smart homes, industrial automations, and wearable devices. Neuroscience research. Neuromorphic hardware is instrumental in advancing our understanding of human cognition. By replicating brain-inspired neural networks, researchers gain insight into the brain inner working, paving the way for breakthroughs in neuroscience. Autonomous systems. Neuromorphic computing enhances the autonomy and intelligence of robots, drones, self-driving cars, and other autonomous systems. Their adaptability and real-time processing capabilities enable safer and more effective operations in complex environments. Brain-machine interfaces (BMIS). Neuromorphic computing drives the development of more effective brain-machine interfaces, facilitating communications between the brain and external devices. This opens new possibilities for individuals with paralysis or neurological disorders. Use cases for neuromorphic computing span both computational and neuroscience approaches. In the computational realm, examples include Intel Labs Lohi 2 chip offering enhanced synaptic capabilities, and the Intel Labs Pohoiki Beach computer boasting millions of neurons for accelerating processing. IBM's True North chip stands out for its energy efficiency, while NeuroRAM showcases offline learning capabilities. On the neuroscience front, the Tygenic chip powers self-driving bike with remarkable agility. The Human Brain Project leverages neuromorphic supercomputers for in-depth brain simulations, while BrainScale integrates biological experimentations with computational analysis. Additionally, Intel collaboration with Cornell University focuses on the teaching neuromorphic chips order identifications, highlights the diverse applications of neuromorphic computing across the computational and neuroscience domains.
Next, let's talk about challenges and limitations in neuromorphic computing. One of the biggest challenges we face is accuracy. While neuromorphic computing is super energy efficient, it hasn't quite proven to be as accurate as traditional methods like deep learning and machine learning. This means we need to work on fine-tuning our algorithms to ensure they deliver the precision we need. However, neuromorphic computers aren't exactly accessible to everyone, and that's a problem. They're still in the early stages of development, and the technology hasn't been made widely available to non experts yet. We need to work on democratizing access to these systems so more people can benefit from their potential. Additionally, we are facing limitations in software algorithms. Most of the software for neuromorphic computing is still catching up with the hardware. We are heavily relying on traditional algorithms designed for older computing architectures, which slows down our progress. We need to shift our mindset and embrace new approaches to unleash the full potential of neuromorphic computing. While neuromorphic computing holds immense promise, we must address these challenges and limitations to fully realize its potential.
The future of neuromorphic computing in AI. Neuromorphic computing is like giving computers a brain, allowing them to think and learn in ways similar to humans. Let's explore what the future holds for this groundbreaking technology. First up, we are looking at how neuromorphic computing is getting better and bigger. As the technology advances, neuromorphic chip will become even more efficient and scalable. Imagine AI systems with supercharged brain capable of handling complex tasks with ease. This means faster, smarter, and more powerful computers at our fingertips. Next, let's talk about real-time learning and adaptations. Just like our brain, future AI systems powered by neuromorphic computing will be able to learn and adapt on the fly. This means they continuously improve themselves based on the world around them. Think of robots that getting better at their tasks over time, or self-driving cars that learn from every journey. Another exciting prospect is the development of brain-inspired algorithms. Researchers are working on creating algorithms that mimic the way our brain processes information. These algorithms will revolutionize tasks like recognizing patterns, understanding language, and making decisions. Get ready for AI that even more intuitive and efficient. Now, let's talk about the fusion of neuromorphic computing and quantum computing. This is like a combining the best of the both worlds. Imagine AI systems that harness the incredible power of quantum computers while maintaining the efficiency and reliability of neuromorphic systems. It's the game changer for AI research and applications. Finally, we need to address the ethical and society implications of neuromorphic AI. As this technology advances, we will face important questions about autonomy, privacy, and ethics. It's crucial that we work together to ensure responsible development and use neuromorphic AI with clear guidelines and regulations in place. The future of neuromorphic computing in AI is incredibly bright. With enhanced efficiency, real-time learning, brain-inspired algorithms, and integration with quantum computing, we are on the brink of the new era of artificial intelligence. But it's important that we proceed this caution, considering the ethical and society implications along the way.
After looking back at the whole discussion on how neuromorphic computing can bridge the gap between biological and artificial intelligence, as in conclusion, neuromorphic computing, a bold approach to artificial intelligence, is modeled after the architecture and operations of the human brain. This research examines its potential to bridge the gap between artificial intelligence and biological systems. Neuromorphic chips enable multiprocessing, event-driven computation, and learning mechanisms that mimic biological intelligence by simulating neural networks found in the brain. This method solves energy consumption issues and opens up opportunities for study in neuroscience, brain-machine interfaces, cognitive computing, and self-driving systems. However, challenges such as specialized software development, benchmarking standards, accessibility, and accuracy certification need to be addressed. Neuromorphic computing is at the forefront of AI advancement, paving the way for transformative technologies. I am JGT Aberatna and
I'm Dilhara Disanayaka. Thank you for watching.